We have learned that helium atoms attract each other due to London dispersion forces. Let's review this and take a closer look at London dispersion forces in general. Remember that London dispersion forces are caused by fluctuations in electron density. As such, they are present between all neutral atoms and molecules. Let's begin by comparing helium and xenon. Both of these elements are noble gases. However, helium has 2 electrons, while xenon has 54. Remember that London dispersion forces are caused by fluctuations in the atom's electron density. We can use each atom's van der Waals radii to look at these fluctuations. The van der Waals radii is half the distance between the atoms at the potential energy minimum, where the forces of attraction and repulsion are equal. These models show that xenon, with 54 electrons, is much larger than helium, with only 2. So xenon will have a much more fluid electron cloud than helium, making it easier to have fluctuations in electron density. To get a better look at the van der Waals radius, check out the figures here. The distance between 2 atoms is measured from each nucleus. This is shown here using the black arrows. The van der Waals radius would be half that distance, shown here by the red arrows. Comparing the arrows side by side, we can see that xenon has a much larger van der Waals radius and will be much more susceptible to fluctuations in its electron density. Remember that intermolecular interactions are caused by the electrostatic attraction and repulsion between atoms. The electrons of one atom will be attracted to the nucleus of another atom. Meanwhile, the electrons of one atom will be repelled by the electrons of the other atom. If atoms have more protons, the nucleus of that atom will be more strongly attracted to the electrons of another atom, meaning that it could have stronger intermolecular interactions. Atoms interacting via London dispersion forces depend on the partial charges that form due to fluctuations in electron density. Partial charges are weak positive or negative charges caused by the unbalanced distribution of the overall charge in an atom or molecule. For the examples on this slide, all of the atoms are electrostatically neutral, but the unequal distribution of the electrons results in part of the atom being more electrostatically negative or positive than other parts of the atom. Consider the atoms of helium and xenon on the top of this slide. In each case, the electrons are roughly evenly spaced out, meaning there are no partial charges present for each atom, and thus no London dispersion forces are existing between them. However, the atoms on the bottom of this slide have an unbalanced distribution of electrons, causing a partial charge to form for each atom. The symbol delta, shown in the title and on the atoms, represent the partial positive and partial negative charges present. In the cases shown on the bottom, a temporary dipole is formed, allowing London dispersion forces to exist between the atoms. The London dispersion forces are represented on this figure using a dotted line. These partial charges on the atoms can happen instantaneously, without any influence from outside forces. Or the partial charges could be induced by interactions with another atom or molecule. Let's take a moment to review. Which do you think has stronger London dispersion forces, neon or argon? The answer here is argon. Being a larger atom, argon's nucleus has a stronger positive charge, making it able to form stronger interactions with other atoms. Also, having a larger van der Waals radius makes it more susceptible to fluctuations in its electron density, meaning it has more possibility for forming a partial positive and partial negative dipole. Now consider this question. Which do you think would have a higher melting point, neon or argon? Argon in this case would have a higher melting point than neon. Since it has stronger interactions between the atoms, it will take more energy to change phase, meaning it will likely have a higher melting point. So in general, London dispersion forces are stronger for bigger atoms and molecules because they have more electrons. London dispersion forces are also stronger for objects with more surface area because they have more opportunities to interact. This could come into play when comparing the strength of the interaction between long, thin molecules and large spherical molecules of the same volume and mass. The long, thin molecule will have more opportunities for intermolecular interaction and thus will have stronger London dispersion forces. Remember that London dispersion forces are just one type of intermolecular force that we will learn about. And remember that intermolecular means between molecules. You must have two or more particles to observe an intermolecular force. Let's take one last opportunity here to check our understanding. Can you explain the relationship between the strength of the interaction between particles and the boiling point? Pause the video here and try to write a claim, a principle that allows you to explain your claim, and the reasoning that connects your claim to the principle. Go ahead and pause the video and try and write a response to this question. As an example response, you could say something like, the boiling point increases as the strength of the interaction between particles increases. When the interactions are stronger, more energy or heat is needed to overcome the interactions and turn a solid into a liquid. Helium actually has a melting point of around 1 Kelvin, and xenon has a melting point of around 161 Kelvin. Was your prediction correct?